1985 and has been working at EDF and subsequently at RTE, which is a French TSO, where he has been one of the persons leading up the R&D part. And he has also been very active in setting up large European projects, for instance, and collaborations between Europe and the US in R&D. And also he has personal experience in supervising PhD thesis within the R&D department at collaboration.
Just carry the whole room. Thank you.
He's a fellow, I believe, and I give you the floor.
Thank you. Yes, the mic is, yeah. Yes, good afternoon and thank you for the invitation. So, yes, good afternoon and thank you for the invitation to be able to share with you some problem I have. So I believe that we are living a big evolution, perhaps a revolution of large electrical system, and I want to share with you this vision. So we are aware that yes, power system, large power system, are very complex machines that have ever been by the humankind. That the National Academy of Engineering of US told that, and the system is becoming even more complex than in the past. So it was already a very complex system, and the complexity is increasing again. So I believe that I want to explain more why I think this complexity is increasing. So no, it's not working. So the outline of my presentation will be a brief description of the European electrical system to show the size of the system, something on RTE, because perhaps I need to explain what is RTE, and something on a conceptual vision of this evolution of our system. And then we want to give you a small example of what we are doing now to tackle this complexity, and then that will give me the opportunity to explain some open questions and challenges by this illustration. And I have a lot of busy slides about that. Let's see if I'm able to share with you all that. So yes, the European system is big. So it's a 36 country and 43 TSOs, and the idea is to have this kind of security of supply at this level, and also to have a kind of economic optimization at this level. So also to have a market at European level to try to share electricity from north to south, east to west, and to use all the possible mix of electricity, hydroelectricity, wind, solar, all over the continent. And there is different synchronous area. We are not sharing the same frequency, and there is a big continental Europe in the middle, and then there is some island around that are connected through DC connections, but everything is connected and we can share a lot of electricity. So the exchange, the physical exchange of capacity, the physical exchange of energy is around the same amount of energy that is injected in France. So it's quite huge. So there is a lot of people around, and so it's a huge, big system that we try to operate as a single system using some kind of market and kind of coordination between TSO in Europe. So RTE is a part of this system. So RTE is a French transmission system operator, and we are a TSO, so we own the asset of the grid and we operate the grid. So we perform the system operation. So I mean that we are managing the grid, but we're also managing in real time the balancing. And of course we are maintaining the grid, and we are offering the access to the grid. We have some contract with all the people who want to be connected to the grid, the customers and the generators, and we develop the grid. So the grid is quite big, so we are operating the grid down to 63 kV. This is why also we are very impacted by this wind and solar power plant, because they are more connected to this level of voltage, and perhaps even on the distribution side, but we are more and more on also on the sub-transmission side. And we have many substations, and we have some dedicated telecommunication system based on fiber optics. So it becomes more and more important for us to because there is some kind of evolution, and we come back on that, on this digitalization of the system. We need a lot of communication, so it's very important for us to have communication, very good communication, and very secure communication. So we have a lot of interconnection with all the country around. So we have different control centers. We have 7 regional control centers, 1 national one, and we create a new kind of organization at European level that is a coordination center between different TSOs. So it's not a hierarchical system, it's just an organization on the side that gives advice to the national control centers. So they have a big vision of the Europe, and they can send advice proactively to the national control center. So it's not an ISO, it's something more a service provider that is able to guide and to coordinate TSOs, but without any binding rules. So it's a kind of, it's a subsidiary for different TSOs, and they are offering services. So in RTE we are very special since the very beginning in EDF. We are developing a lot of tools internally, all the decision support tools. We are developing everything from system adequacy to any kind of network analysis. We are developing all these kind of tools internally and all the EMS. We believe that the modeling of the system and the tools are very important to understand what we are doing. So it's very difficult for us to believe that we can manage the grid using some black box. And we need to understand at least the modeling of the system that is used in the decision making, and perhaps also the kind of method that are used to optimize or to simulate the grid. So we are also a kind of enabler of new market design. We develop this new concept of market grouping in Europe. At the very beginning, there was one market by country, more or less, and then we coupled the market. And at the beginning, the grid was just modelized by some ATC, some kind of constraint between hubs, and then we put a more advanced model called flow-based model that try to take care a bit more accurately of the grid in this coupling. We developed in France a kind of market-based capacity mechanism, because now we know that all the short-term market couldn't give the right signal for the investment and generation. So we try to develop a mechanism to push people to invest for the future on the generation side. And so RT was a promoter of this, an enabler of that. And on the demand side also we developed something very in 2015. Yes, on this demand side management, and we are one of the first in Europe at this time. Now it's not anymore the case. Okay. I don't know. Is it working? No. No. And the batteries.
Yeah.
Demand
side management.
I don't know.
The operator.
So I don't know where's the battery. Yes. Interesting. Okay. So batteries. Is working? No? Yes? Okay, good. So some key figure about RTE. France is still exporting. So there are the figure of 2016, but they are more or less the same now. So we are still exporting more than we are importing, even if a lot of countries around have a lot of wind and solar. We still have some nuclear power plants that are producing electricity during the night and as base load. So the total energy injected in France is quite large. So we had a peak in France that was around 100 gigawatt. So the money we have, so we have a turnover of more than 4 billion, and we invest a lot, 1.5 billion. And we don't build a lot of line, but they are very costly because we have to go underground and to use HVDC technologies. So each time you build a line, you can pay for 1 billion for, I don't know, for example, the interconnection between France and Spain costs 7 million euro just for 60 kilometers and 2 gigawatt, but 60 kilometers under the mountain, and we have to dig a dedicated tunnel for that. So it's very huge. And so we have something very specific. So we have some budget for R&D, and only for R&D is why I'm here, and I have some time to to spend to interact with academia. And so we are lucky. We have a budget that is around 35 million euro each year, and we have around 120 people that are working R&D with a big D, because we are developing a lot of tools. And and so our customers, so we RTE operates the high voltage grid. So there is still some industrial customers in France, less and less, but there is still some big factories, and we hope to keep them in the grid, and so this is a big challenge. So we have, of course, also these big generators, many nuclear power plants. But we have also these railway companies that are directly connected to the high voltage grid. And of course, we have all the distribution companies that are connected to the grid. And we have also some players that are no physical asset, they are just market participants. And we have some contract with them and on different kind of mechanism. So this is what was the system, what is the system, and now we have this kind of big evolution of the system, perhaps a revolution. So of course, all the people are thinking of this intermittency of renewable energy, but I want to focus on something else. So I want to focus on the fact that this renewable energy have nearly no cost, no marginal cost. So the fuel is for free. Yes, yes. So we have to think about that. And something else that is very interesting, they are connected through power electronics to the system. We understand that when you have PV panels, nothing is moving in that this kind of thing. So we are creating a frequency by some kind of electronic devices, and is very controllable, but it's very different. So we have to think about that. So I think we need to rethink how to protect, control, and optimize this power system because of these two different dimensions, economics and dynamics. And something that is even more interesting, because of this low controllability of the res, of the renewable energy, we can think of using new method to try to balance the system. We can think of storage and electrical battery, for example, or demand response, and to have some response that could be sensitive to price. But once again, it's very different from what we found in the old test book, when we say that it was not possible to store electricity and to have demand that was not flexible and not dependent on price. So I think there is urgent need to rethink about this power system economics and dynamics. And now, for the last decade, we have more or less do some kind of incremental change, and we try to patch the system to be as close as possible to the previous one. But I think it's perhaps not a good idea. Now we have to perhaps to review a lot of things, perhaps even on the market, on the regulatory framework. And of course, we have to think about this migration path, because this is a huge system. It's not possible to change everything in one night. So even if I am against this kind of marginal adaptation, I think we need to think about this migration path, even if we need to rethink totally the system. So the complexity is increasing a lot. I like to have these three dimensions, the spatial complexity. So we can have some cities, some smart buildings that can be more autonomous, and they want to have zero energy or perhaps positive energy, so they could inject power or energy in the system. We have the national level or perhaps the regional level, and then we have the European level, and we have to deal with this kind of different scale in space. Of course, we have a different scale in time. We can have milliseconds to decades, and the energy policy, of course, is something that is impacting a lot what we are doing, because the short-term market is not saying that we need to shut down the nuclear power plant in 10 years. So we have to think about that, and so we have some uncertainties on the energy policies, and that will impact a lot all the dimension more for the planning. But and of course we have the stochastic dimension. Of course we always have the weather condition, because we have the lightning on all the assets that are outside, and of course we have the wind and the sun that are changing the generation and the load, and of course we have this behavior of the consumer that could change, and we can have electrical cars or whatever that could change a lot the load. So all these things increase a lot the complexity. And something that is happening also to try to tackle this complexity is to put more digital solution to do that. And also the energy transition push to more dispersed generation and distributed control. So we need to assure the safe, secure operation and efficient operation of this large power system, but now we have to manage a large population of devices or agents which have some kind of partial autonomy. They want to decide locally based on some kind of local optimization. Rather than in the past, they were more or less passive. Now they can make decisions locally that could impact the system. And in the past, I believe that the cyber layer was more a kind of, the digital layer was more a kind of optimization layer. So the physics was leading the stability of the system and everything. Or if there is some control, they were quite simple or quite analog local control. But now with all this power electronics, a part of the physics is impacted by the control of these power electronics. So there is a part of the digital things that are the blue part, that are very embedded in the physics and must be defined in order to ensure the stability and the safety of the system. So the blue digital is not the same as the yellow one, so we have to think about that. So the requirement could be very different, is what I want to explain here, is that for me, I use the term of more optimization. So I think that we don't have to mix feasibility and optimality. So of course, we can have digital solutions for many things, but they can have different requirements and different certificates. For example, if I have a kind of system like that, it's an illustrative, naive example for sure. So the system can live in this domain for all the time. So we can have an operating point in the system. So we can choose an optimal solution for that. But anyway, but then of course we can have some contingency, because it's not possible to design a system that is able to sustain any contingency, because the cost will be just impossible to afford. So some contingency will bring the operating point outside. So we need some control to bring back in a very secure and manner the point inside the feasible domain. So for that, we need to have certificate verification and security assessment, and to assess what is the largest possible contingency we can deal with, what is the uncertainty set, because this point, this star and circle are some kind of balls around, because there are some kind of uncertainties. And of course we need to have very secure and some certificate on that. But when we are inside, we can use any kind of market or whatever to find a new optimal solution. And of course we can rely on any kind of new ideas, peer-to-peer blockchain or whatever, demand side management or smart building or using smart meters or whatever. But for me, there is two different dimensions in that, and we don't have to mix the two. And I think it's very important to be aware of that. Of course, there is a kind of fuzzy limit between the two. It's not black and white, but I think it's interesting to think about that, to think that I don't want to rely on the blockchain and Madame Michu in France to protect a transformer. Yes, I don't want to have an explosion transformer because a customer is not at home and is not able to change the consumption to protect a transformer. For sure, I don't want to do that. So let's go to kind of an example what we want to do or what we are doing on an area in France. We try to minimize the curtailment of wind power in one pocket of the sub-transmission network. So it's a northwest of France, yes. So the idea is that it's a sub-transmission level, so it's a 90 kV network. So the idea is that we don't want to upgrade the system, we don't want to have grid expansion, not only because it's expensive, it's because the people don't want this ugly tower in the landscape, and that take a long time to do that. Anyway, we have to go to very different administrative layers and a lot of discussion around, so it's not only a question of money, it's a question of acceptability, but even for money, perhaps, is try to use the existing asset as much as possible. So we want to keep a mesh operation of the grid because it's good to have different connection, because we are more robust, we can have a tripping of a line and we can continue to have electricity. For the voltage is good, for the losses is good, so we try to keep the mesh operation of the grid as much as possible, and we try to develop a control that take care of this area. So it's a distributed control around this 12 substation, and to try to optimize the system at this level. So the idea is that we want to take care of the system using all the flexibility we have. First of all, we want to take into account the fact that we have when we have a lot of wind to export from this area, we hope that we have some cooling effect on the line. So there is this dynamic rating that the capacity of the line, of course, are depending on the wind and the cooling effect of the wind. So we can use this dynamic rating to use as much as possible the existing capacity. So in this area it's quite flat, so it's quite easy to develop some kind of forecast locally, and we have put some weather sensors all around the area, and we are able to predict quite well the weather and to anticipate a bit for a few minutes or the wind. So we are able to expand the capacity compared to something that is more static and more independent on the wind condition. And then we try to minimize the curtailment of the wind power, taking into account the fact that we can switch the breaker in substation. So in substation we have some connection that we can split the node. We can have different buses, we can have different electrical buses, and we can change the flows on the grid using this kind of dynamic switching. So the idea is that we want to use, we are using some model predictive control to do that. So the idea is to use this kind of control to be able to, yes, to use as much as possible the existing capacity without grid expansion, yes. So this is a kind of conceptual vision that we want to use for other things. So we want to install some batteries also to do that in other part of the grid. So the idea is that we want to have a new kind of level. So it's a hierarchical control. So we have the control centers that try to optimize, to define some kind of optimal trajectory. We have this control at the area level that try to follow the trajectory and to adapt to the contingencies. And it will be something around 1 second. The first one will be around 5 minutes. And then at the substation level, we want to keep some protection to avoid some kind of safety problem. And we want to develop a new idea of distributed control based on the middleware. And we are a member now of this Linux Foundation for Energy to develop this middleware as a framework for this distributed control. But one open question, the first one, is when we put this kind of advanced control in a system, how to take into account this control in a central process, in a centralized operational and market processes. So of course we believe that this idea to go to more edge computing, to a more distribution, is in line with the complexity, because we are more and more things to deal with. In the past we have one nuclear power plant was 1 gigawatt if we at the very high level voltage. Now perhaps we can have 100 wind farm in the subtransmission network. So for dispatcher, for the operator in the control room, the size of the problem is changing a lot. So we believe that we need to help the operator to do something to have some automatic controls that take care of that locally. So we think that grid flexibility have a lot of value. There is a nice webinar from Schmoll Orange from Berkeley that explains something in this line. So I'm very happy with that because I'm pushing this idea that grid flexibility is very important. So this webinar is very interesting to put some value on that. So the difficult problem is how to have a model of this local control in the upper layers. So we have a kind of generic answer that is a bit fuzzy, but it's a kind of hierarchical control using some proxies. So what I mean by proxies is a kind of simplified abstraction. So at the upper level, at the coordination level, we need to define an optimal trajectory, but we need to have a kind of modeling of this local control. It's not possible to have a full model of all this local control, but perhaps it's very possible, or it's a question mark at least, to have an abstraction that is good enough to define this optimal trajectory. And of course, it's the same at the area level. We need to have a proxy of the protection that is at the substation level. So this is the idea of proxies, and I think it's a key word that I borrow from Louise, that the idea that the complexity is huge, and we have to decompose the thing and to go to some edge computing, distributed control, and to have some abstraction of that to be able to tackle the complexity. So I will, in the next slide, I will give some kind of open question around this different dimension of this problem. First of all, I have the same dimension that the modeling of uncertainty is a critical point. Perhaps we need more closed-loop control. So this is perhaps we need to understand what is this coordination layer and what the operator are doing in this case, and then perhaps something on the market design and regulatory framework. So on the modeling of uncertainties, so of course we need to have some accurate forecast, but of course we need some modeling around the yes, it's not only the expected values that we want something more, because if we want to perform some risk assessment or some kind of robust optimization or something, we need something more than just the expectation. And of course we need to take some decision in advance, because some action need time to be implemented. For example, if we want to have to postpone a maintenance in the grid, we need to decide that a few hours before, to try to use a crew to do something else in other part of the grid. Or it's the same if we want to have a generator that must be on, we must decide that perhaps 8 hours before or 6 hours before, depending on the technology of the generators. So we need to make decision before real time, and sometimes long time before real time. So we have a lot of uncertainties, and we need to make decision in this context. And uncertainties, once again, are not the fluctuation of the wind. They are the forecast errors. And of course they are depending on the forecasting method. For example, we can have very interesting, nice negative correlation if the weather conditions are wrong, but we have more wind in one area and less wind in another one. It could be nice for the balancing of the system. So we can have very interesting negative correlation that has nothing to do with the wind variation, but more on how the weather forecast are done. So we have to think about that. And once again, forecast is just, there is different method, and there is always this trade-off between bias and variance. So it's always possible to, yes, depending on the forecasting method, the uncertainty will change. So, of course, it's very important to capture the spatial and temporal correlation when you are performing grid management. I mean, the spatial correlation between the local uncertainties, I mean, at the nodal, at the bus level. And of course, we can have different modeling of these uncertainties, and depending on what you want to do, what kind of decision we want to make, and what is the associated problem, we can find different kind of framework to do that could be more suitable or not. So there is a large number of methods, so we need help to understand this method and to understand what are the best for different type of problems. So I've listed some method, but And want to insist on that. It was more or less my question, that some measurement of some variable are not purely random variables. They are impacted by some existing policy. For example, if we are performing some demand side management, or if some people are performing some demand side management, and you are not aware of that, so when you are measuring when we are measuring the load and we want to forecast the load, if we don't know that, we are in trouble. So we need to understand what will be if the demand side management will not be active, or it will be acting another way. So we have to perform this counterfactual, this what-if analysis to do something. So we don't know exactly how to do that, and it's very difficult, and perhaps we don't have the full information to do that. It's the same for the wind power curtailment. If someone is performing some wind power curtailment, for example, in a distribution system, and we are not aware of that, we have a new kind of variability that impact the system. It's the same for the maintenance of for the wind farm, for example. We see that sometimes there is some wind turbines that are stopped because of some problem or because they are in maintenance. So there is a new kind of variability that is not a purely random process. Perhaps it could be designed by some policy. So we need to understand how to take into account this kind of effect, and it's not very easy. For example, I have an example. Yes, I have a small example that is very simplistic, but anyway, what we call load in a transmission, in fact, there are some kind of power flow transformers like that. So, for example, in the substation, we have two loads, and in fact, in distribution, they can change the topology. So when you plot for example, the PDF of this load, you have two modes. And you don't know if, and when you try to forecast locally something, you're in trouble because we don't know the topology, so we don't know what to do. And so we need to do something. And once again, it could be this kind of bimodal distribution that could add more complexity in any kind of robust optimization, and we have to deal with this kind of complexity. Yes. So more closed-loop control. So I believe that when the level of uncertainty increase, any kind of open-loop approach will take more and more margin to operate the system, because it's impossible to do something else. But so perhaps it's good to think of something else. And also, if we try to compute something, we must rely on even to compute the margin we need. It's a very complex optimization problem with this kind of stochastic programming, and with discrete variable and non-convexity for example, if you want to deal with voltage and reactive power, so it's very, very difficult. And if we want to keep the operator in the loop, the best that they can do is they can act in 1 minute to take one action. So it will be very difficult to do more than that. So it will be nearly impossible to coordinate multi-control. For example, if you want to change the topology and the phase shifter transformer, and to curtail a bit wind, and to store a bit energy in the storage, so it will be impossible for them to do that. So the coordination will be a challenge if we keep the men in the loop. So I think that closed-loop control could seem a good option. So on Thursday, Florian and Emiliano will give something on that. So, and of course, Steven is working on that with a lot of people on this more closed-loop optimization for power system. And I understand that fast sampling rates allow control to use very simplified model, in fact. If the sensitivity are good, if you have the right sensitivity between the control and the variable you want, you want to control, is good enough. So you can use perhaps a kind of model-free control, more or less, and you are able to do something. And of course, you are able to react to uncertainties. But of course, if you go to some centralized implementation, perhaps it's difficult because of this cybersecurity, and for example, and also the problem that you're using a lot of communication network. So if there is a reliability issue on the telecommunication, you are in trouble. And also because of the migration path, we have a lot of legacy ICT system, so it's very difficult to improve everything in one day. So something distributed could be perhaps better. So of course distributed control is a nice idea, and I believe that we can make analogy with some complex system. For example, the interaction between the eyes and the brain. The eyes are now sending all the information to the central brain with all the spectrum and everything. In fact, the brain is sending an information of what you want to see, and then the eyes are compressing some information that is sending back to the brain. So this is an idea I think that is quite interesting for complex system. That it's not a good idea to send all the information to the central location, but to compress the information locally and to process locally things rather than to send everything to the central location. Of course, if we are doing some distributed control, we need to define, yes, of course we can have a priority on some specific area, some windy area, something like that, where we can develop new ideas that we don't have to deploy all over the system, but just in this very specific area. And of course, we have to define some independent area, but once again, it's not impossible, I think, because it's more about the sensitivity. The sensitivity must be good enough to be computed locally, and if the sensitivity are not too much dependent on the external network, it's okay. Even if the external network has some impact on the internal network, but they can be treated more as perturbation if they are not impacting the sensitivity of the local network. Of course, we still believe that I still believe that we need some slow coordination, because locally we don't know exactly what to do, and we have to implement, of course, all the market things and all the things that we want to do. And for example, if we have some outage management and we are able to forecast that, we have to inform the local control. Of course, we have some problem, because this discrete control about the breakers are not fully compatible with this idea of this small step approach, that to say, okay, I have more or less a model-free thing, I just perform a small step and then I wait for the measurement to understand what to do. Of course, if you adjust this discrete variable, it's very difficult to do that. So we have to think more about that. Of course, there is always this problem of active and reactive power, and is it a good idea to try to mix everything in a single problem, or is it good to keep some kind of decoupling or not? And of course, it will be, for example, very possible just to take care first of the thermal limit and the current and everything, using perhaps some approximation to avoid some voltage issue, and then to have another control that take care of the voltage. Of course, we can think of some kind of robust MPC to be able to deal with that, but of course we need to have all the standard question about the MPC things, that of course we have all this kind of final cost and final constraint to be sure there's some kind of property of this MPC that sometimes are not easy to define. And if you go to AC, we have this non-convexity, so we have the discrete variable and the nonlinear coupling, and so it's doubly non-convex, in fact, somewhere. So we have to deal with that. So it's very complex and could be very computationally intensive and not possible for control power to do that. And the last point is my favorite one, is of course, if I have this very advanced control, I need an abstraction of this control in the upper layer. So I need to send a model of that, or to define a model of that for the upper layer. So I need to define, using perhaps some machine learning techniques, using some Monte Carlo simulation, what could be a good model for the upper layer. So we can also develop some kind of more formal ideas, more around control and reachability analysis or things like that, or robust inner approximation of maximal invariance set. We try to develop some idea like that, but it's not very scalable, and it's very. But anyway, we need to think how to have a model of this complex advanced control in the central decision making. This is what I have here. So of course this. Why we need this coordination layer? Because some people believe that we can go to fully distributed system with no central decision. I believe that perhaps it's not the case. We always have to implement it some kind of market anyway, set point, or to follow this set point. So, and the upper layer knows that, so they have a better weather forecast. Yes, they know the outage, the planned outage. They know the generation schedule, and of course they can define a local, an optimal trajectory for the local controller. But taking into account the capability and the limitation of the capability through these proxies. And of course they can coordinate, if needed, through this set point, through this trajectory, the different local controller. So, and then I want to try to share with you some idea about the operator, what the operator are doing now in this context and what they will do. So on the first step, we can try just to have an evolution of the current practice. So we can just try to have a more advanced security assessment. So the idea is that the operator are defining some trajectory, and then we can assess using very advanced tools what are the risks associated to this trajectory. And then they can decide to change that. It's just a kind of simulation-based decision making with the operators that choose the right decision. So we had a big project called GARPU, and we was the technical director of this project that tried to define what could be a new kind of reliability criteria going behind N-1. So in power system we have this old traditional N-1 idea that we want to keep the system safe if we have only one element that is out the system, that is stripped. So one generator, one line, and but with this wind and power system, this wind and this wind and solar power, so we know that it's a bit crazy perhaps to do that because depending on the wind, for example, if you have a wind farm of 100 megawatt, we know that in average that will produce perhaps 30. So perhaps it's not a good idea to build two lines of 100. So perhaps if we build two lines of 50, perhaps it's enough. But of course, if we have some problem, if we have bad luck and we have a tripping of a line and the wind is more than the average, the speed of the wind, so we'll have a problem. But so perhaps it's an acceptable case, but we have to think about that. It's not anymore N-1 independently of the system state. We have a coupling between the probability to be in the state and the probability of failure that is new. So in GARPU they try to develop some new idea around that. So there is a website and there is a lot of documentation, but of course the idea is to go to some more probabilistic security assessment, but of course the computational burden is large, so we need some screening technique to be able to implement that. So the idea is that we can use machine learning to do that. So we can, the idea is to speed up some computationally intensive simulation by learning offline or from past analysis. So we are always performing this kind of security assessment all the time, each 5 minutes. So we have a lot of data, so perhaps we can learn from this data at least a kind of screening techniques. And we developed some new idea recently on this possibility of super generalization. Using these proxies, if you are smart enough to have a smart encoding of the topology in the network, in a known network in this case, we were able to simulate N-2 quite accurately, even if N-2 was not in the learning set. So it's very interesting, and there is some kind of possible super generalization of neural networks that can be useful for this kind of probabilistic security assessment to assess what would be the impact of N-2 that is nearly impossible to do using any kind of computation now. So the second step could be to have an imitation of the operators. So they will have the security assessments and they will make decisions based on that. So we can learn from what they are doing without understanding too much what they are doing, but they are doing something. And then we can propose back this decision for them in the future, and of course we can assess the risk to before proposing this decision. So it's quite easy to sell to the operator because it's very. We can perhaps find some similar condition in the past where they did that, so it's quite explainable, or at least they can trust more than say, okay, in the past someone did that and it was a good solution. So we have the same validation with the same security assessment engine. So, and something that could be more interesting, and we have a new PhD on that, so to have this kind of loop, perhaps we can gather the feedback of the operator from the decision we propose, and then we can use this feedback to improve again the imitation of the decision-making process. So this is a new term that is socially guided machine learning to take the feedback of the operator in the learning stage to improve that. And perhaps we can have a kind of assistant and to have a natural language processing to have an easy interaction with the operator, not to push them to select something in a MMI or something. Perhaps we can have an interaction that would be more a vocal interaction with the operators. So we have and then of course after that we can have an optimal decision-making process that. But we believe that it will be anyway a mixture between mathematical programming and reinforcement learning, and something that, and we can think of many different aspects to inject machine learning in the process. So we can have some proxy using some kind of machine learning to imitate some very complex optimization, or inside the algorithm we can select how to perform relaxation or to add cuts, for example, using machine learning. And anyway, we'll validate with the same security assessment. The problem is more is it explainable for the operators? And this is one big topic, how to explain this kind of very complex black box for the operators, and to find a kind of storytelling at least that can be useful for them, or at least they can trust. So on the market part, yes, yeah, it's over. Yes. So on the market part, so I think that any market design or regulatory framework we normally should push us to use as much as possible the existing asset. So in the context of this intermittent generation, to avoid us to overbuild the grid, because it's easy for us if we build a lot of line, of course. we don't have any problem, but perhaps it's not a good idea for society. But we need to find a way to put value on these grid flexibilities. And unfortunately, it's not really the case. So now, at least in Europe, so for example, as a TSO, we have some money if we build new assets. So we have the capex are very rewarded, and we have a return on capex, and the opex are very bad, and the regulatory body pushes us to reduce as much as possible all the opex. So it's very bad because it's very difficult for us to put some value on these flexibilities. And it's easier for us to try to build a line rather than to put a new sensors or new computers in a substation. So I think it's not very good. And then there is something else that for me is important, that the consensus in this power system economics, all the people believe that locational marginal price, which are kind of dual variable on optimization, are a good way to set the price for the market participant. I'm not so sure about that, because unfortunately the true problem is very non-convex in many sense. And if I want to add this grid flexibility, for example the switching, I bring even more non-convexity in the problem. So I have a lot of questions about the variability, the spatial variability of this price, when the topology of the grid could change, and it's a degree of freedom of this optimization problem. So even if you are performing a convex relaxation of this problem, the Lagrange multiplier of this convex optimization has nothing to do what the people want to do in this location of the grid, because we choose the topology as it's not the fault of the people, and we can do whatever we want. So it can be your fault or your fault for this line congestion, because I can choose the topology. So perhaps we have to think again about this local marginal pricing. And once again, I'm not against optimization. In EDF, and we were performing optimization much before any kind of market. Yes, Carpentier defined this ACOPF in the 60s, so it was much before any kind of optimization or any kind of market. But I'm against the spatial variability of the price when you are dealing with the topology. And the same for the wind and solar curtailment, power curtailment. It's not very clear for me what to do with that, because there's no fuel. The fuel is provided by nature, so then it's difficult to understand what is the price of when you curtail the wind, or you curtail some wind farm or PV farm, or what would be the cost for that. So I think there is a urgent need for reviewing all this market design and regulatory framework. And perhaps we just, I put some idea like that just to be a bit provocative, and perhaps we can split the problem in different steps, and we can use a kind of market clearing to using a kind of simplification, kind of simplified abstraction of the grid, but including all these possible flexibilities. So it's more a proxy that we say to the market, if you are in this kind of space, we are able to manage the grid. And then we can have a congestion management that could be more a collaborative process, for example, between TSO and Europe. Then we try to minimize the adjustment of the load and generation schedule, taking into account all the grid flexibility and all the fine detailed model of that. That will be very non-convex. And then we can have an ex-post allocation, of course, some benefits based on some what-if analysis inspired by some Schweppe value ideas but we have some time. It can be an ex-post, it's not a real-time process. We can perform a lot of computation, and we can deal with some kind of what-if analysis. We can, for example, we can say, we can relax all the constraints on the line in one country. What happened? We can say that the phase shifter in Belgium are not acting. What is the value of that? So we can develop some kind of simulation to put some kind of metrics to develop some idea to allocate the cost and benefits of this kind of mechanism. So this is my conclusion. Thank you for your attention. Yes,
Patrick, Janusz Bialek, Skoltek. Patrick, you are one of the leading figure, of course, in RT pushing R&D and etc. But in my experience, system operators are mostly motivated by fear of change, by conservatism.
yes.
Because, of course, the worst thing that happens is a blackout. So now, if you introduce more sophisticated methods, you mentioned, among other things, closed-loop feedback, something working with Stephen, and Florian is working on that, or transmission switching, you are pushing more towards the boundary. And so in theory everything works fine, but in practice it may work not so well, and then there is a blackout and the chief executive goes in front of national TV and has to explain why things work. So normally the progress is in markets, for example, is the mixture of greed and fear.
Yes.
And there is a balance between.
But it's nobody pushing. So I am the one that's pushing. And there was a lot of...
For the system operators, is clearly fear, but there is no greed because you don't make money directly out of it.
Yes, this is what so we need to put some value on this grid flexibility. Yes, in some way. I don't know exactly how. We need to reward the risk taker in a TSO community. I think
what would push systems, now comes the question, what would push system operators like RT and others towards adopting those more sophisticated methods which would get more value out of the grid? Because there is nothing more simple than n-1. You just leave it on and then you sure it'll be safe.
Yes, of course.
But it's expensive.
Yes.
So how do you get this additional value? How do you push system operators to adopt?
We need to explain that to the regulatory body. The regulatory body must be more technical, as they must understand that there is a lot of value on these grid flexibilities, and to push to have more incentive regulation based on some kind of, I don't know exactly what, but not on capex only. Yes, you know, it's completely crazy to push people just to be line without thinking of adding new control. So for me, it's a kind of mistake for society. It's kind of and all the people are speaking of digitalization, and you know, it's exactly what I am speaking about. It's digitalization of the power system. We put more sensors, more control, and less copper and less hardware. So this is exactly what we want to do. So I think we can use this kind of fuzzy or this kind of new buzzword about digitalization and to be smart and to be. But of course, the regulatory body must push, of course. But RTE is very singular, and we know that, and perhaps China also could help us to. to show that it's very possible to do very advanced control and things like that. But of course, the regulatory body must think how to reward the TSOs that are smart, or I don't know, that want to take risk, or I don't know. But I don't know how. But we need to train and to educate the regulatory body. So if you can do that.
Maybe a comment, but
yeah.
So you need possibly new methods in order to value these new sources of flexibility and compare it with the cost and so on. But you also need data to plug in it into these methods to compute the size of the numbers. And this is probably where we are quite weak.
Yes. Yes, for me, I'm finding always to be more and more transparent, because for me there is a kind of it's a kind of thing that is mandatory for a kind of monopoly that is a monopoly. We are the only ones that doing this kind of business in France. Nobody understands what we are doing. so we need to be very transparent, to be challenged by you, for example, the university, academia, and of course, perhaps 80% of the time, your challenges were not very interesting, but perhaps 20% of the time it will be very interesting, and to push us to improve something, because we are no competitors, so we can become lazy and so I think transparency for me is very important. But I am from the R&D. For the operational people, they don't like too much to explain everything and to. You know, sometimes it's very complex, and they make decisions under uncertainties, and there is always ex post is very easy to explain that it was a wrong decision, but upfront is sometimes difficult to. But they are afraid of transparency. I understand why, and some people now use this kind of cybersecurity and privacy as some kind of argument to avoid to exchange data. But I say okay. For me, you know, at the transmission level, the privacy. Of course, we can have some factories that don't want to give the full curve of the electricity consumption, because if you see that, you know what they are doing, how they are processing curve. For example, car manufacturer, for example, they don't want us to provide the electrical demand in very fine grain, because starting from that you can assess how many cars they are building, and so of course I understand that, but we did a lot of job on this project in US and this grid data, and we have a lot of discussion with Stephen and Pascal on that, and perhaps this idea of creating some kind of synthetic but realistic enough data could be interesting, and and we have to fight against the legal department, so sometimes they don't understand too much the technical details. So perhaps what we can train some neural network using the very accurate data, and then we can provide a neural network that is able to generate something that is very similar to what is the reality, but we are not providing the data, we are just providing a neural network that is able to generate the data. So using some auto-encoding stuff or something like that to generate some data starting from a white noise and something like that. So, but anyway, we have some issue, and I agree that it's a big problem to assess something. And if you go to, because if you have to have some numbers, it is 1, 10, 1 billion, yes, this is a problem. Even if you know that it's a positive impact. Is it a small one or is it a big one? Of course, it's very depending on the data, yes. Yeah.
I think one last question, because it's time for tea.
Anthony, or I don't know.
I'll be quick. You talked about, I'll be quick and predictable. You talked about topological control as something that undermines the rationale of locational marginal pricing. I might be wrong with this, but my understanding is that, at least in Europe, but also in the US, topological control is largely used in Europe more for redispatching, in the US, as far as I understand, for contingency response. So day-ahead integration of topology control with the rest of the optimization is not really, as far as I understand, something that's done currently either in Europe or in the United States, which would then...
No, it's done since a long time in DDF, for example, or in RTE. So, for example, around the big nuclear power plant, when we are 5 of them connected, we open the bus bar coupler, for example, and doing that, we avoid to overbid the grid. So it was done in the very beginning. So we are using this, and for example, at the borders between Germany and France, we have a substation. We are splitting the substation into electrical buses in coordination with the phase shifter transformer in the other side of the Europe to manage the loop flow in this area, and we are doing that routinely. And of course, we change the congestion management. The congestion can be moved from one line to another one. And the customer
yes.
or the price will change a lot depending on that.
The essence of my question is, at what stage of the day or the decision-making process do you do that? How far from real time?
We can do that even in real time if we. It's more.
Exactly.
For example, CORESO, this kind of coordination center. This is the objective of this coordination center, to be able to assess the impact of that and not to push the problem in other parts of Europe, but to reduce the problem, because it's very easy to push a problem in another grid rather than to solve it. So the idea of this coordination center is to try to use all this degree of freedom in a kind of fair way, not to push a problem in other part of the system.
So it's a real-time reaction to the real-time conditions of the system, which would suggest that when you're doing planning in the day ahead, there's no reason why the worry about day-ahead transmission switching action should affect day-ahead pricing. So I don't
know. I believe that they are performing N-1 in this market clearing. And we are able to handle N-1 doing this kind of corrective control using switching. So good luck if you want to formulate this problem as a convex optimization. You can try, but then even if you have a convex relaxation and then you find the optimum, so the dual variable of this problem, nothing to do with any kind of signal for the people, because the people are not responsible to be. And for me, it's more, I am very against this local marginal pricing since a long time, because for me it's a bit
okay,
strange. Yeah.
I think this is a very interesting
yeah,
discussion.
But we can continue, but we already have this
just let me
discussion
say
for many times.
I think in the next presentation the data will speak about this problem. So, and then we can further discuss, of course, for 4 months about these kind of problems and try to find solutions.
Miss 4 months? Oh.
Okay. Have a nice tea.